last time, what did we do? Integral, right? The definition of the integral. And I think we all agreed that we really enjoy calculating unit sums and finding the limit. So maybe that's just where I'll stop, and that's how I'll make you take every integral. Oh no, see, no one's disagreeing with me. So there we go. My semester's done. Great. It's a pain in the ass. Right, actually, integration in general, even without the definition, is a massive pain. You'll study that way more in Calc 2, but in general, integration is way harder than differentiation. Speaking of, we have been studying derivatives. Right? Well, just about every operation you can think of doesn't have an opposite operation. Like addition, subtraction, multiplication, division, raising something to a power, taking the radical, exponential, logarithm, trig, inverse trig. So wouldn't it make sense that the derivative has an opposite as well? So something to undo a derivative.
The antiderivative?
This is called the antiderivative. Typically, antiderivative will be represented with a capital letter. So we say that big F is an antiderivative of little f if big F prime is equal to little f. But what's the derivative of a constant?
Sure.
So what do you think will happen if I add an arbitrary constant to big F? It doesn't change the fact of an antiderivative, does it? Which means every function that has an antiderivative, because as we'll see, not all functions have an analytic antiderivative. In fact, probably 99% of the functions that exist do not have antiderivatives, which is a pain.
Like what?
My favorite is e to the minus x squared. That has no antiderivative. There is no function that gives e to the minus x squared as a derivative. So if a function does happen to have an antiderivative, it has an infinite number of them. We call that a family of antiderivatives, which leads into the general form of an antiderivative. Right, so big F is an antiderivative. For every constant big C, so is big F plus C. Right, so this is saying that every antiderivative, you can add a constant to it, and there's still an antiderivative. If G is an antiderivative, there is a constant for which G of X is big F plus C. This means that the most general form of an antiderivative is big F of X plus a constant C. By the way, part 2 is also saying that antiderivatives are unique up to a constant. So with the exception of the constants, antiderivatives are unique. There's only one. The notation used is an integral notation, because as we're going to see, integrals are related to antiderivatives. Right, so indefinite integral is an antiderivative. Right, so generally speaking, the act of finding an antiderivative is called integrating f. So if I ask you to find the antiderivative of the left, it's the same thing as saying integrate the left, find the integral of f. But again, by definition, it is an antiderivative, not an integral. Integration has a specific meaning. It's mapping a function to a constant. Right, as we saw, it's an area. I mentioned this, it's a family of antiderivatives, which allows you to create some pretty cool plots called integral curves. All you do is you just plot all the different curves in the family. You get some pretty cool looking shapes out of it. So I can probably actually just skip this and go right here. This you may want to copy onto your reference sheet.
Right.
Right, so this table is giving you the differentiation formulas that we studied before, along with their corresponding integral formulas. So the integral of a constant is k times x. Power rule for integration. As long as n is not -1, the integral of x to the n plus 1 over n plus 1. So you add 1 to the power and divide by that new power. The derivative of 1 over x, or not derivative, sorry, the integral of 1 over x is the log of the absolute value of x. That is very commonly forgotten, the absolute value. Right, and I'm not going to go through all of them, but you get the general idea. I do want to point something out, though. Do you see the integral of secant on there? What about tangent? Cosecant? Cotangent? They're not basic integral forms. They actually do require a special technique to find. These are only the basic forms. I may, if I have time, derive.
Sorry, I don't understand.
Sorry. British accent?
Yeah. Kind of make it valid.
Very posh. If I have time, I may derive integrals for secant, tangent, cosecant, cotangent. Because we will learn the technique to be able to do that this semester. I don't think log of x is on here either. It's not. That, technically, we can't do until Calc 2. Although I do think they just tell you what it is in this book. I think it's section 5.7. I think I remember seeing it. But as to why that is, you won't know.
What's here?
That's a good question. And same thing with the inverse traits. Inverse traits do have antiderivatives. It's just you're going to need Calc 2 to derive it. Right, and then that's just kind of saying, yeah, maybe just once you find the antiderivative, take its derivative to make sure you get back to the original function. So properties of the integral, these are kind of all the same. You can split it across addition and subtraction. Right, you can pull out a constant multiple. So antiderivative is linear. Who has or is currently taking a mechanics course, intro mechanics, which is physics 1? I'm actually surprised. No, well, if you don't like physics, then pretty soon this term is going to become a nightmare. Initial value problems. Actually, this might become a nightmare when you take differential equations. So the differential equation is an equation that involves functions and their derivatives. We will only look at the most basic forms of differential equations, i.e. dy dx equals a function, or second derivative equals something. You'll learn more about solving more advanced differential equations much later. So let's say you're given a differential equation. So again, we'll just assume dy dx is equal to something, f of x. Well, the solution would be the integral of f of x, right? But it's a family of solutions, right? Because it's for any constant c. You can't find that constant c unless you're given an initial value. Like y of x naught is equal to something. Then you can find c. That is an initial value problem. The condition you're given is generally just called an initial value. So I could say y of 2 equals 8. That is called an initial value, even though it's really not. Y of 0 would be the initial value. I would call y of 2 a boundary condition, but that's just me. All right, so let's go ahead and start finding antiderivatives. I'm going to start from the definition. So if we're looking for a function whose derivative is 6x squared minus 5. So I'm not going to use those formulas for this problem. We'll go over it conceptually through the actual definition of an antiderivative. So what you want to do is, okay, 6x squared minus 5. What function, when you take its derivative, is 6x squared minus 5?
2x cubed minus 5x plus c.
Right, so I ignore the constant for now, and at the end I then go, okay, so there's my antiderivative. Now add any constant to it. By the way, that is called the simple antiderivative. It's just the one where the constant is equal to 0. Right, so generally speaking, that's how I always solve integration problems, like find the simple first, and then add a constant at the end. Now just check it. Take that derivative. Do you get 6x squared minus 5? There is your general antiderivative. So again, we want a function that when we take its derivative gives 4 root x plus 3 over x squared. Well, just go piece by piece. 4 root x. What function has 4 root x as its derivative? Sounds right. Just take its derivative real quick. X to the 1/2, so you get the right power. Yeah, 3 over 3 is 1, 8 over 3 is 4. There's your anti. What function has derivative 3 over x squared? Well, you know it's going to be something over x, because differentiation reduces your power by 1. So when you go to take that derivative, it's going to be -1 times some constant times x to the -2. What do you have to multiply -1 by to get 3? Now just add your constant at the end. There's your antiderivative. And again, just check it, right? Take the derivative, make sure you get back to 4 root x plus 3 over x squared. What function has derivative cosine of x? What function has derivative 7e to the x?
70 dx.
And now add your constant. And just check. Take its derivative. Derivative sine, cosine. Derivative 7e to the x, 7e to the x. Derivative of a constant, 0. That's your antiderivative. So that's just kind of doing it conceptually, right, without memorizing the formulas. This is great for simple functions. Once you start to get more complex, trying to do it that way is kind of a pain. That's okay, because you'll learn a lot of techniques next semester in the algebra. Oh, yay! Right, so we're told that f prime is 3x squared plus 4x minus 1. F of 0 has to be 5. We need to find f of x. Now, a comment on notation. You always need your differential. The proper syntax is that. Parentheses around the integrand, especially if it's attached to addition and subtraction. Because that's saying that the dx applies to every single term. It's applying that entire term. How often do you think you use integrals in applications? Just about all the time. So we get lazy and not write the parentheses. It's understood that the dx is going to that whole thing. So if I revert to being lazy and not writing the parentheses, just note that those parentheses are implied. With the antiderivative notation, I'll do it for this problem, just like I did with derivatives, and then I will not do this again. Right, so you can split it across addition and subtraction, so you have 3 different antiderivatives. And you can now factor out and again, this is very common. Just writing it as dx, not 1dx. Factor out the constant multiples. Because now what we do is go, okay, so that's going to be 3 times, now what is the antiderivative of x squared? What are you missing?
Let's see.
I'm going to call it C1. I'm going to show you why I just wait to the very end. What is the antiderivative of x? Power rule. Add 1 to the power and divide by that.
Square root over 2 plus c.
What is the antiderivative of dx?
X plus c.
Now simplify. So what's going to wind up happening? We're going to have an x cubed, right? Plus 3c1. We'll have what? 2x squared plus 4c2 minus x minus c3. C1's a constant though, isn't it? What's 3 times a constant?
Another constant.
It's called C4. When in doubt, C4. Oh, but C2 is a constant, right? What's 4 times a constant? It's called C5. I'll keep that as minus C3. And I'll just make a note. Isn't addition commutative and associative? So we can group it however we want, right? So I can do that, right? Oh. What's a constant plus a constant? What's a constant minus a constant?
A constant.
Isn't that whole thing just a constant? Call it C6. Or actually, let's just call it C. That's why I just wait to the very end. All your constants are just going to get absorbed anyway. But that's why. All the constants will be absorbed into one constant. That's the antiderivative. In case you forgot, that's after that. But we're told f of 0 has to equal something. Has to be 5. Well, plug in 0. What's 0 cubed? What's 0 squared? What's 0 plus 0? Well, actually, I guess I should say what's 2 times 0 first. And then 0 plus 0 minus 0. Oh, doesn't that have to equal 5? That means C is 5. There's a solution to the initial value problem. Initial value problems will have one unique solution. Yeah, another IVP. Initial value problem. This one, is with respect to time, because this is probably a physics type problem. We're told that dy dt is 2t minus 1 over t. We're also told that y of 1 is 3. We're also told that t is greater than 0. We want to solve it. What do you get for 2t? What's your anti?
T squared.
What about for 1 over t?
So it's ln the absolute value of t plus c.
Oh, wait a minute. What do we know about t?
It's greater than 0.
Which means I can ignore the absolute value. And then plus some arbitrary constant at the end. There's the antiderivative. Why is 1 though? What's 1 squared?
1.
What's natural log of 1? So isn't that just 1 plus 8? What does that have to equal?
So c equals 2.
Not 2. Yes. Mean c is 2. And so our function t squared minus log of t plus 2. Show, okay, so we have little f is 2x. Big F1, x squared plus 1. Big F2 is x squared minus 5. First, they want us to show that both of those are antiderivatives. Now, what does it mean to be an antiderivative?
The derivative of the other function.
What's the derivative of f prime? Or f1, sorry.
2x. Also 2x.
So they are both both antiderivatives. Now they want us to find f1 minus f2. What's that? Now, what does that mean? F1 and F2 are differing only by a constant, which is illustrating that any two antiderivatives of a function differ only by a constant, which is the same as saying antiderivatives are unique up to a constant. Physics. Particle moves along a line with velocity measured in meters per second, given by v of t equals 4t minus 3. Its position is initially 10 meters. Find an expression for the object's position at time t. What is velocity? It's just change in position with respect to time, right? What are we given?
Position, initial.
Which means what? S of what?
S of 0.
And what is it?
10 meters.
There's your IDP. That's all. And so velocity or position would be the antiderivative of velocity. What's that antiderivative?
2t squared minus 3t plus c.
But we're told S of 0. From the function that we just found, what's S of 0?
C.
Just C.
Just c. Right.
What does that have to be?
10.
Free fall. An object that is in free fall. It is only under the influence of gravity. Does free fall actually exist?
No, because there's always air resistance.
However, there are times where we can ignore air resistance because it's negligible. Also, interesting tidbit of information. Satellites, they orbit the Earth, right? They're actually in free fall. Orbit is actually just free fall. Yeah. It's just free fall. It's falling. It's just, you have to look at it 2 dimensions. Its horizontal motion is fast enough so that it kind of matches its vertical motion. So it's falling, but it's also going, so it's never actually hitting Earth, but it's still in free fall. So if you're ever in orbit, you can say you're falling style. So we're just going to take an object. It's given an initial velocity v naught at an initial position y naught. We're considering it is in free fall. If some object with initial height y naught, and it's given some kind of initial velocity. This will be in free fall. Its only influence is gravity. Right? Then what is its acceleration?
-g.
-g. You actually will consider air resistance. You'll re-examine free fall in differential equations, and you actually do it, consider air resistance. I don't think you do it in intro mechanics. In fact, I'm almost positive you will not cover it in intro mechanics. You will touch upon it, though, in Newtonian mechanics if you're a physics major, which is a level 300 course. All right. Our goal is to describe the motion of this object. Well, it's velocity. Isn't that just the antiderivative of acceleration? Right? Because acceleration is the rate of change of velocity. But what do we say acceleration is? Just -g. What is that antiderivative?
-gx or gt plus c.
It's called C1. But what did we say its initial velocity was? It's v naught, right? But what is v of 0 of the function?
C1.
Therefore, the velocity is described as v naught minus gt. But velocity is itself a rate of change of what?
Attention.
What is that antiderivative?
V naught t minus g squared t over 2. Oh, sorry, gt squared over 2 plus c2.
What's s of 0 of that function?
That's not.
Of the function.
C2.
And it has to equal what?
That's not.
That is the height. I actually should be using y because that's what I gave. It typically free falls with a y because we're only considering one dimension. That is your free fall model. This is the equation of free fall motion. I guess that means I can now ask you questions on free fall. You will actually re-examine this in Calc 3, except it's no longer called free fall, it's called projectile motion. So that's where you now also consider the horizontal. Now, air resistance you still won't do in Calc 3. That is, believe it or not, air resistance is way more complicated than you think. Even differential equations, all they do is they say air resistance is proportional to velocity, which it's not. Well, that technically is, but you have to also consider surface area. And that's just drag. That's not friction. That's not, I'm sorry, kinetic versus static friction, which is even worse. Then you have rolling friction you have to worry about. If you're a mechanical engineer, you have the friction from objects rubbing on each other. That sounds so wrong, but nobody jokes. That's awful. Questions on the antiderivative? Fairly straightforward.
Are we going to go into, so just to clarify, we're not going to go into like more in-depth antiderivatives this semester?
The most in-depth we get is chain rule.
I was going to say, we're not going to do like any like product rule stuff.
That is complicated.
Okay, cool.
Actually, I lied. The most complicated you might see would require you to use trig identities. So like maybe a sine squared times cosine to the 5th power.
Okay.
You could do that using trig identities and new stuff. Even though they typically cover that in Calc 2, it's not really a Calc 2 course account. So I do touch upon it. That would probably be the most complicated when you have to use a trig identity.
Okay.
Second would be use of. Everything else I'm going to leave for Calc 2.
Tabular method.
I'm not familiar with that method.
Oh.
Oh, is that reading a table?
What?
Tabular, is that just reading a table?
No,
I guess not.
it's like a polynomial times a trig function. Or e to the x times a trig function.
Oh, that's integration by parts.
Yeah.
That's the, what is it called? The lie rule.
I learned at the tabular method.
Why do they have to come up with new names for things?
Sounds good.
So it is Thursday. Specifically, it's the Thursday before a week off. I unfortunately have work tomorrow. But I do have to be up at 4 p.m. So. Again, this thing, I'll